Welcome back to the wonderful world of astronomy. This is Chapter 18, The Bizarre Stellar Graveyard, Part 2 on neutron stars. Remember the big picture as we studied in Chapter 17, The Life of Stars, whether low or intermediate or high mass stars, what they end up as eventually. And we saw that low mass stars and intermediate mass stars, they become white dwarfs, and that was the topic of the first video in Chapter 18. And high mass stars become either neutron stars or black holes. Only the most massive, extreme few become black holes, but most high mass stars become neutron stars, and that's what the topic of this video is. So let's look at what is a neutron star. This is actually a picture taken in X-ray of the hot gas bubble that has been expelled in a supernova from a star, and at the center is the neutron star. A neutron star is the ball of neutrons left behind by a massive star supernova. Remember back in Chapter 17 we looked at a high mass star. When it gets to the end of its life, the core becomes iron, and it collapses into a ball of neutrons, and the outer layers of the star are expelled out in the supernova. Degeneracy pressure, actually what's called neutron degeneracy pressure, supports a neutron star against gravity, and it is very, very highly compressed. It is the leftover core of a high mass star, but it's a few miles across, about the size of a small city. The process that created this ball of neutrons is shown in this picture here. Electron degeneracy pressure goes away because electrons combine with protons, making neutrons and neutrinos. And so those neutrinos are these elusive little particles that are flying throughout the cosmos. So whenever you have a supernova, among other things, just the general life of stars, neutrinos are always pouring out from them. But I want to focus here on the major product that's formed. When a proton and electron combine, it becomes a neutron. And so this ball of neutrons collapses together and becomes a neutron star. How were neutron stars discovered? It was 1967, and at Cambridge University, an astrophysics PhD student named Jocelyn Bell, she was doing radio astronomy and saw something very peculiar out there in space. Pointing the radio telescope in a certain direction, there were pulses of radio waves, and they were very precisely timed, 1.337301 seconds apart, where you can see in this graph the intensity would spike every 1.337 seconds, and it was very regular, and it was perplexing. What is this thing that we've just seen? The pulses were coming from a spinning neutron star, and it was called a pulsar. And so they didn't know about neutron stars at the time. When they finally figured it out after a few years what this thing was, they started calling it a pulsar, and then they realized it was a spinning neutron star. This is another one. This is a time-lapse image of the pulsar in the heart of the Crab Nebula, the remnants of a massive star supernova. And so this one is much quicker. Every pulse is 0.033 seconds, so about 3/100ths of a second. And something that pulses this quickly, these are often referred to as millisecond pulsars. So here's what's going on with a pulsar. A pulsar is a neutron star that beams radiation along a magnetic axis that is not aligned with the rotation axis. And so here you've got the neutron star, here's its axis of rotation. It's got a magnetic field similar to the Earth's magnetic field, although trillions of times stronger because of its highly compressed state. And emanating from the poles, from the magnetic poles, is a beam of radio waves, so going through the North Pole and the South Pole. And notice those magnetic poles are not lined up with the axis of rotation. And the Earth does that as well. Its magnetic poles are not lined up with the poles of its rotation. And so when this spins, if the observer, such as Earth, happens to be in direct line of the beam of radio, then every time it rotates, we're going to see a pulse. Now, this is an artist's conception, making this analogy between a neutron star in the sky with its radio waves going out from the North and South Pole, and also a lighthouse. The radiation beams sweep through space like a lighthouse, like lighthouse beams as the neutron star rotates. So if you're near the beach, if you're offshore and you're looking, you see a lighthouse. In the distance, you just see a pulse of light as the lighthouse, as the lamp rotates. Every time it sweeps over you, you see a pulse, and then another pulse, and then another pulse. Well, the lamp itself is not pulsing, it's just rotating. And those pulses, you're interpreting them as pulses of light from every time the beam sweeps over you. And that's what's going on with a pulsar. Pulsars spin very fast, sometimes many times per thousandth of a second, or per hundredths of a second at least. They spin fast because a stellar core's spin speeds up as it collapses into a neutron star. It's a good example of conservation of angular momentum, and this relates to, you see the figure skater who is spinning, and then she pulls her arms in, and by conservation of angular momentum, as her size decreases, her speed increases. And that's what happens immensely when a core of a star contracts down to just a few miles across. Maybe when it was a star, it was rotating every month or two, and now it'll rotate many times per second. What can happen to a neutron star in a close binary system? And this painting might look familiar. It's the same picture I showed in the previous video with a white dwarf. And so remember, here we have a situation where there's a giant on the left, and it's grown so much that its outer layers are more attracted to, and in the last video I said to the white dwarf, but now the same thing can happen with a neutron star. Matter falling toward a neutron star forms an accretion disk, just as in a white dwarf binary. Accreting matter adds angular momentum to a neutron star, increasing its spin. Matter accreting onto a neutron star can eventually become hot enough for helium fusion. Now, this is exactly what I described in the previous video with a white dwarf. The same thing can happen. If that hydrogen builds up enough, it can fuse into helium. It's just, the only difference really is that everything that happens with a neutron star is much more dramatic just because of the higher gravity. And so this sudden onset of fusion produces a burst of X-rays. And here we have the light curve of such a, what's called an X-ray burst. This is X-ray intensity and versus time. And so you can see is after the moment of fusion, within just a couple of seconds, there's a sharp increase, a burst of X-rays, and then it eventually dwindles down. So it's a very quick thing. But we see this in the sky as a burst of X-rays coming from a neutron star. So they call them X-ray bursts. And that is the end. Short section, but that's it for neutron stars. So what have we learned? What is a neutron star? It's a ball of neutrons left over from a massive star supernova and supported by neutron degeneracy pressure. How were neutron stars discovered? Beams of radiation from a rotating neutron star sweep through space like lighthouse beams, making them appear to pulse. Observations of these pulses were the first evidence for neutron stars. What can happen to a neutron star in a close binary system? The accretion disk around a neutron star can become hot enough to produce X-rays, making the system an X-ray binary. Sudden fusion events periodically occur on the surface of an accreting neutron star, producing X-ray bursts. And that is the end of our section on neutron stars. I hope you have a great day.